Today in class we talked about the law of conservation of mass. So we went back in the lab and you had some baking soda and you had some vinegar and you mixed them together, and hopefully if you did the lab correctly you found that the total mass of the products, what you ended up with, was the same as what you started out with. So the reactant's mass was equal to the product's mass. Alright, so in a slightly different example, if you had sulfur, 32 grams of sulfur, and you mixed that with 56 grams of iron, and you added heat, you would end up with a product known as iron sulfide. Well, if you knew the masses of the substances that you started out with, you should end up with 32 plus 56 grams, and you should end up with 88 grams of iron sulfide. So it's always the case, if we're taking account of every atom that gets produced, that the mass of the reactants is equal to the mass of the products. We can't gain or destroy mass when we're doing chemical reactions. So this is true of the total mass of a macroscopic system. It's also true of the mass of each element, of each atom that we see here. So as an example here, I'm mixing two gases together and there's going to be a chemical reaction, and as you can see I have 4 blue atoms on the right side and 4 blue atoms on the left, and then I have the same number of white atoms on the right as I have white atoms on the left. So they're reforming, they're recombining, but the total number is always going to be the same, so the total mass is always going to be the same. So I just wanted to recap that a little bit for you after class, but today we're going to talk about something just a little different, and that is the law of definite proportions. And the law of definite proportions basically talks about how elements in a compound are combining. So again, this is what 17th and 18th and 19th century scientists were doing before they really knew that much about atoms. They were discovering that you have definite proportions that the atoms are combining in. So if you have H2O, you're always going to have twice as many hydrogen atoms as oxygen atoms. But the percent mass composition is always going to be the same because you have that fixed ratio. You're always going to have 2 hydrogen atoms for every 1 oxygen atom. Since hydrogen and oxygen atoms have the same mass on average throughout the universe, you're going to have the same ratios of the mass. So let's just work through a few examples here. But first we'll go over our formula for percent mass composition, which is the mass percent of one element in your compound is the mass of that element divided by the total mass times 100%. Now for these problems, sometimes you're going to be given the masses that you can just plug into this equation. Other times you're going to have to look on the periodic table. So as you see, as your periodic table of the elements, it has squares for each element, and you have your elemental symbol in the middle, your atomic symbol, and then above that you have what's called the atomic number. Now we're not really going to worry about that number just yet. What we want to worry about is the number at the bottom. It usually is expressed to a certain number of decimal points, and that's the atomic mass. That's the mass of one atom. And it's usually expressed in atomic mass units. You can convert it to grams. We'll go over that a little bit later in the year. But this is the number that you're going to have to worry about when we do these sorts of problems. So let's go over a few examples. So our first example, we have an unknown compound. We don't know what the compound is, but we know we have 78.0 grams of it, and we know that in order to create it, we put in 12.4 grams of hydrogen. So we want to know the percent mass of hydrogen in the compound. So again, we're just going to use our formula. The percent mass of the element is the mass of the element divided by the total mass times 100%. And we just plug in our numbers. Since we used 12.4 grams of hydrogen to make 78.0 grams of this compound, we're just going to divide 12.4 grams by 78.0 grams and then multiply that by 100%. And so we're going to get 15.897, but we only know this to how many sig figs? 3. So we know it to 3 sig figs, and so we have to round to 15.9%. All right, so let's look at another example which is slightly more complicated. So this example, it's going to ask the percent mass composition of phosphorus in phosphorus trichloride. So again, in this case, we don't have masses given, so we're going to have to look up masses on the periodic table. And for this problem, we're just going to assume that we're talking about a single atom. But because all phosphorus trichloride molecules are the same, you'll get the same mass percent for 1 atom or 2 atoms or 3 atoms or 12 atoms or a million atoms. So we can just pretend that we have 1 atom of this substance, and it's going to be the same percent mass composition no matter how many atoms we have. So like I said, we got to look at our periodic table. So here is the periodic table block for helium, and as we can see, we need to look at this number at the bottom to determine our mass. So here are phosphorus and chlorine. So the mass of an atom of chlorine is 30.974, and we measure that in what's called atomic mass units, AMU. And then the mass of chlorine is 35.453 AMU. So the percent phosphorus is the mass of phosphorus divided by the total mass times 100%. So the mass of phosphorus in 1 atom of phosphorus trichloride is, 1 molecule of phosphorus trichloride is just 30.974 because we have 1 atom of phosphorus in our total molecule. And then our total mass is the mass of phosphorus, so 30.974, plus the mass of chlorine that we have in our compound. Now, for here, we have to multiply that 35.453 AMU times 3 because we have 3 atoms of chlorine. So this is the mass of 1 atom, and since we have 3 atoms in our compound, we have to multiply that number by 3. So you take the 30.974 AMU is 1 atom of phosphorus, and then the bottom is the 1 atom of phosphorus plus the 3 atoms of chlorine that it takes to make up this molecule, and then we multiply that by 100%. The AMUs cancel. Our answer is going to be in percents, and so our answer is 22.554 24.554 percent. All right, so that wraps up our lesson. If you have any questions on any step, just put a star next to it, and hopefully we'll get to that question on Monday. We'll be running practice problems in class, and you can feel free to ask any questions you have. That's all for now. I hope to see you all on Monday.